In this video, we are going to get introduced to a new topic, which is flows on the circle. Okay. So, if you remember, a few lectures back, I have mentioned that for 1D flow system, the oscillations are not possible, right? So, in today's lecture, what we are going to do is we are going to contradict that statement, okay, which means the oscillations are possible. The only difference is for that system and the system which we are going to see under this topic, flows on the circle, is that which is the following. Okay, so for example, what we have seen earlier is flows on the line, okay, and where this is how we have the system dynamics, and this x belongs to a real space, right? And in the flows on the circle, we are going to introduce the dynamics in the following manner. With theta dot is equal to some function of theta, okay, and again theta is in real space, but it can take any angle between or any value between, let's say, so it belongs to 0, 2 pi. So one side it's closed, one side it's open. Okay. So and one more thing is, this function f should be periodic. Okay. So f is with 2 pi as the period. Okay, 2 pi as the period. Okay, so what does that mean? It means f of theta should be equal to f of theta plus 2 pi. Okay, so if a function is in this manner and I can take any value for theta only from theta to 2 pi, or in this set, then I could call this system as a system which is flowing on the circle, okay, instead of flowing on the line. So here if we see, there will be a real axis like this, and this thing and this thing are extended, right? And this is how we define the x. But here what do we do is, say there is a circle, okay, and then that circle, so each point represents some theta, okay, some theta which is this angle, okay, and along this, in this circle, the system will flow. So that's what this flows on the circle means. Okay, so whatever the field, the trajectory we will be drawing, our phase portrait will be drawing, we will be drawing it in this circle. Okay, we could also do it by taking this circle and map it to this real axis, but the thing is, we will be considering, so let's say I'll be mapping it into a real axis, but I will be considering only from maybe 0 to pi or sometimes depends on my convenience from minus pi to pi. Okay, so that's how I will do the analysis for the flows on the circle. Okay, let's see an example. Okay, before the example, I will also mention why it's periodic. Sorry, why this system is periodic is because once it starts from somewhere, this point, and goes and changes its state variable because of the dynamics, and when it comes back, okay, you could either call that as 2 pi or 0. Okay, so therefore we are considering this as an oscillatory behavior. Okay, fine, let's see one example. So the example which we want to say is theta dot is equal to sine theta. So this is our function. Now for this function, how the system is going to behave. Okay, so if we sketch this, so let's plot it. So if we plot this function theta dot equal to sine theta, this is the function, but what we do is we just limit our window within this range from, let's say, minus pi to pi. Okay, you could also do the same between 0 to 2 pi. So I'm just using it. Okay, I'm just using this range. Fine. And if you see, this is minus pi and this is pi, and this is the flow, and if you look, the dynamics is periodic, yeah, the f of theta is periodic. After it reaches pi, it starts from here. Okay, it will go, and once again it will go from here. Okay, so yeah, this is the dynamics, and this is theta and this is theta dot, and if we see here, the theta is going to, in this range, the theta is going to decrease, right? So because theta dot is negative, so it's going to go in this direction, and here theta dot is positive, so it's going to go in this direction, and this point is a fixed point, which is a stable fixed point or unstable fixed point. So just give a little disturbance and check, and you will get to know that it's a unstable fixed point. So all the calculations and everything is as same as the flow on the line. Okay, and is there any other fixed point? And yes, one is here and another one is here. The thing is, we are not going to consider that as two more fixed points. This fixed point and this fixed point are same. Okay, so if you see it in the circle, let me try to draw one more circle. Okay, fine. So one is minus pi, which is this point. Okay, another one is pi, which is also this point. Okay, that represents the same point in the circle, and another one, theta is equal to 0, represents this point, right? And in this point we have observed that this is a in theta is equal to 0, that's a fixed point which is an unstable fixed point. So instead of putting a solid, we will be putting it like this, and this notation is also as same as in the flow on the line. And this one, is it is it stable or unstable? Let's check that in the picture. So if you see here, it's going towards this point, okay, and if you see here, this is also going towards the same point. This point and this point are same, okay. So in both, both sides it's getting attracted, so it's an attractor or a stable fixed point. So we are going to represent that by putting a solid dot, okay, and the arrow mark which we are going to put it in this manner. So here it will go in this direction, and here it will go in this direction, okay. So this is how we draw the phase portrait, okay, fine. So that's one example, and if that's getting confused to imagine that this and this are the same fixed point, try imagine the following thing, okay. Cut out this piece of rectangle, okay, and then what you do is you just make a cylinder out of this rectangular piece. So the way you are going to make the cylinder is by joining this edge of the rectangle and this edge of the rectangle, okay. And if you do that, then this point and this point will merge, okay, and as time goes on, all you have to do is you just rotate the cylinder and you just see the dynamics. So when you imagine like that, you will be able to observe that this point and this point are nothing but the same, okay, this point and this point, okay. So that's one example. Let's see another example. So in another example, let's say theta dot, which is equal to just theta. Let's make it further simple, okay. Now whether this function is a or whether this system is a flow on the circle. Actually no, because let's plot it, okay. So this is the one and this is that line, and if you see here, this line has some value at theta is equal to minus pi, and it has some other value when theta is equal to pi, okay. When you cut out the cylinder and join it, you will not see this as a continuous line, okay. There will be a jump at theta is equal to pi or minus pi, okay. And because of that reason, this is not a flow on the circle. The system is not a flow on the circle, okay. So yeah, so that's one example which is not a flow on the circle. and in further videos we'll see some more examples and some physical examples, right? Thank you.